I'm Asma Sattar, and today I present our paper Context-Aware Graph Convolutional Autoencoder. I will start with the introduction of recommended systems. Recommended systems are information filtering systems that suggest useful resources to the users based on their preferences. For example, Netflix for the movie recommendation. Here key elements are users, items, and rating metrics. Graph neural network treat this problem as a link prediction in bipartite graph, which is further approached as matrix completion. Graph neural network learns from the local and global structure of the graph to produce the node representation with learning objective that if two nodes are linked with each other, they have similar representation. And their higher challenges includes that recommender systems keep on expanding as new users and new products come to the system, and individuals involved in the network has dynamic behavior which affects user opinion on the products. This is the thing which we are going to investigate in our work. Typically, graph neural network based matrix completion approaches treat this problem as a 2D matrix, which gives us a bipartite graph between users and items, and edges are labeled with the user opinion. But we believe that user's opinion highly impacted by the context, and context can be any dynamic attribute, for example, location, time, time of the day, and company of the user. In our setting, this gives us a 3D matrix between users, items, and context, with users and items have some static profile and context has some dynamic attributes, and this gives us a bipartite graph between users and the products in such a way that now edges are labeled with the opinion and context information. How can we effectively integrate these three kind of information, rating, context, and user item features in our model? Next, I will explain the architecture of our model. We have extended the graph convolution autoencoder, which work on 2D matrix between user and item, to integrate the context information on the edges. In this green box, as shown that this is the input data, we have the following input data. We have user to item opinion matrices, AR. Basically, these are the R matrices. Each AR contains the user to item pair if they are connected with respect to rating R. We have user to static feature matrix and item to static feature matrix. Then we have a 3D matrix which contain the context representation between the user and item, which represent under which context user has provided their opinion. Then we have done the statistical analysis on training data to get these matrices, which is UC and VC. This contained information that which context is more important for the user, like under which context user give the maximum rating. Similarly, we have the IVC, which contain under which context product get maximum rating. So which are the favorite contexts for the users and the items. We have provided this input data to our encoder. Further, our encoder contain the weight sharing GCN for the user to item matrices, and then rating matrices, which is the opinion, and then we have graph convolution network for the context matrix, and then we have two dense neural networks for the static features as well as context importance features for the user to item. Then we have concatenated these representations, and we get from the encoder we get the final representation, which are the concatenation of these all kind of matrices, and then we provided this to our decoder, which reconstruct the matrix between the user and item to give us a link between user to item, which is the labeled link, and then we get the reconstruction loss. Next, I will explain the encoder of our model. Basically, in order to model the user's opinion, we have a customized weight sharing GCN, which allows us to send the message to the neighbors based on the rating on the edge. As shown in the equation, we have a weight matrix WR for propagating the message from the edge. In order to model the user and item content feature, we have used the dense neural network. Originally, we have 3D matrix between the user, item, and context, which basically represent the context information between the user and the item when user provided the opinion. So what we did is basically we normalized the context information by dividing each context to the total number of contexts between user and the items, and then we have accumulated this information. We have get this final accumulated information. We pass this to the our simplest graph convolution network to get the context aware representation for the both user and the item. But due to accumulation, we lost the importance of the context, which varies from person to person. In order to in order to map this kind of dynamic preferences. What I mean by the dynamic preferences or the contextual importance varies from person to person is that basically one might want to have a romantic movie with the partner, but one might want to have animated movie with the children. So user is connected to the both animated as well as romantic movies, but it's because of the company that it prefers to have a romantic movie instead of having the animated movie. So in order to have mapping this kind of dynamic preferences, what we did is that we have a statistical analysis on our data. We have used the same AUVC, which is basically 3D matrix between the user, item and context, and then we have alpha importance factor, which actually gives the more importance to the context, which is which under which user has given a maximum rating, and less to the context, which get less rating between the user to item. And here NU is total neighbors of the user. Here this term NCUVI basically total context between user to item. And then we have, after getting this UC information, we pass it to the dense neural network to get the representation final for the user. We did similar for the item to get under which context item get maximum rating, and we have used the same alpha importance factor there as well. After getting this representation with respect to the context, with respect to the static content features and the user opinion, we have concatenated this representations, and then a final representation are passed to our decoder. The decoder in our setting is similar to the one we extended with the graph convolution autoencoder. Here we use similarly a probability distribution over all the classes, where UI and VJ are the representation of the user item which we get from the decoder. QRR as the R learnable matrices, and we get the probability distribution over all the rating classes. We have R is equal to 5 in our case. We have compared the performance of our proposed approach on three publicly available data sets with respect to mean absolute error and root mean square error. Aldos, Komora, and DePaul are movie dataset. Travel STS is the strip dataset. We have compared with the following baseline, out of which four are the matrix factorization approaches, and one is very recent graph neural network approach for the for the user to item and user to user graphs, and the last one is graph convolutional autoencoder for the 2D matrix between user and the item. We have tested our algorithm in two settings. First one is context impact on the opinion, and another one is context impact on the features. We have improved the result with respect to the baseline algorithms. This is because if we compare to the probabilistic metric factorization and the biased MF, they do not consider any side information, so that's why they perform not so much better than if we compare to the other social MF and the SVG++. They incorporate the collaborative signals, but still they are not integrating the context information which affect the collaborative signal and the opinions of the users. Then if we compare to the GCMC and graph REC, we can see that these are the recent approaches which are with respect to the graph and which are based on the neural network for graphs and graph neural network. We are performing better on these two approaches as compared to these two approaches as well. So in order to prove our point that the alpha importance factor matters, basically alpha is a factor which gives more importance to the context which are basically important for the user and under which the item get good rating. It gives more importance to that context. We have seen that without the alpha we have get more error as compared to when we have incorporated alpha in our model. Finally, I will conclude my presentation. In this work, we have highlighted the importance of prioritizing the context and the context information. Basically, prioritizing the information of the context for the user item affect positively to the opinion. So that's what we have studied here, and we know that from this study that dynamic preferences in graph neural network works well. We showed that prioritizing the favorite context can have the positive impact on the performance. In this work, we have accumulated the context information, but in future we want to investigate that what if we have a separate embedding for the user and the item context, and what if we have allow the user to item to interact multiple times with each other with different context. So we want to have this kind of investigation. We will definitely go in details in our future to investigate these things. Our code for our model is available on this Git, or we have provided the link. You can go and check it out. Thank you for listening me. If you have any question, you are welcome. You can email me. Thank you.